All right, we're back with video 2. This time we're going to talk about exponential decay. So the last video, we got a real example of exponential growth when we invested $100 into a savings account with 5.5% interest. This time around, we're going to look at a real example of exponential decay. So what happens when you start out with a population of something and it exponentially gets smaller. Big idea here is a half-life. That's what we're going to use for our example. Vocabulary, we're going to try to well define exponential growth and exponential decay. So let's get started with what exactly a half-life is. So the half-life of a radioactive substance is the amount of time it takes for half the substance to change from its original radioactive state to a non-radioactive state by emitting energy in the form of radiation. It's a science term. It's from chemistry. But what we're talking about here is a half-life is the amount of times it takes for the amount of a substance to reduce by half. So in this case, we can actually model that as a function. A of t is equal to P, the initial population you have present, times half to the power of T over H. That models the amount of material present at some given time T, and H is whatever that half-life amount of time is. So let's rewrite that here using our pen tool, and we're going to say, so this is the function A of T. It's the amount of material present for some given time T. It's equal to your initial amount present times that factor of 1/2 to the power of T over H. So T is some given time T, H is the half-life. All right, well, let's take a look at that in the next slide. So, example 3. Suppose the half-life of a certain radioactive substance is 20 days and 5 grams are present initially. When will there be only 1 gram of the substance remaining? When will we just have 1 gram left? So what I want to do first, before we get into Desmos, you see the link down there at the bottom, is at least try to reason through the problem a little bit. So we start out with 5 grams. We'll say that's at day 0. Let's say day 0. On day 20, the amount of time for the half-life, we have remaining now 5 times a half. And so we don't have the initial amount present, 5 grams. Now we have 5 halves grams present. And then another half-life can go. So another 20 days. Now we're up to day 40. And following that same sort of pattern as we did with the money, we're going to multiply by that factor again. So this time now it's 5 times a half squared. And so now we no longer have 5 halves grams present. We have 5/4 grams or 1.25 grams present. So let's think about that in a model. Going with that formula from the previous slide, A of t is going to be equal to 5, the initial amount present, times our decay factor, 1/2, to the power of T over the half-life, which is 20. And we want to know when we have 1 gram of the substance remaining. So when is this, the amount left, equal to 1? Well, one way we can do that is solving it graphically. We can let a y1 be equal to this function here, a of t, and then we can let a y2 be equal to 1, and wherever they intersect, that's where we're going to have the amount that we're talking, or the time where we have 1 gram left. So I'm going to clear that and get back to my mouse pointer and click over here to the Desmos graph, and you can follow along with me. Over to this slide. So you should be there now. So here we have it. Y is equal to 5 times 1/2 to the power of x over 20. And then we've got y is equal to 1. we see that those do intersect. Desmos is great. Here we just click on the graphs and they already have a grade point there. Let's click on it. So the X value where they intersect is 46.439. So at about 46 and a half days-ish, we have 1 gram remaining. So we solved that one graphically. I liked looking at it that way. So let's go back over to our slideshow and let's move on to the next slide. It's definitions. We've got exponential growth. We've got exponential decay. Exponential growth first. The function y equals k times a to the x, where k is positive, is a model for exponential growth if a is greater than 1. That's the big idea there. So if your growth factor or decay factor is greater than 1, your function is going to show exponential growth. However, if that number, that a, the growth or decay factor, is between 0 and 1, now you're talking about exponential decay. And so I'm going to pull up the pen tool again, and I want to show you if a is greater than 1, then we are looking at a model of exponential growth. Our function is increasing. Our amount present is getting larger exponentially day by day, or hour by hour, or minute by minute. If that exponential factor is between 0 and 1, say it's a fraction, it's a half, like half-life, it's a fourth, it's a third, it's 5/6, anything that's going to be between 0 and 1, then we're talking exponential decay. So we're getting smaller and smaller in amount present, and that function is going to be decreasing. So here we've had 2 good examples of real-life exponential growth, real-life exponential decay. There are a lot of ways that we can talk about exponential growth and decay in real-world scenarios. We already did interest investments. We already talked about radioactive decay. It's good in population growth. Lots of different applications there. So answer the question that follows, and I'll see you on video 3.